Hello, everyone, and welcome to an Open Hardware Foundation webinar. My name is Mike Thompson. I'm the Director of Verification with the Open Hardware Foundation. And today it is my very great pleasure to introduce Massimiliano Giometti, who will be giving us a talk entitled From Trust Me to Check Me, Open Verification for RISC-V High Assurance Silicon. And this is a very interesting topic for the Open Hardware Foundation. Max will be talking a lot about the state of open source and the state of open source verification tools, and also physical implementation tools, which are all very near and dear to our hearts in the Open Hardware Foundation. Just a quick introduction to your speaker today. Massimiliano's first professional love was communication systems, coincidentally, also mine. But in 2018, a career shift led him to the world of computer architecture, enabled through RISC-V, which also mirrors my career path as well. So, driven by a lifelong passion for sharing knowledge and a fascination with the open source ecosystem, Max co-founded PlanV in 2022 to bridge the gap between open source hardware and industrial silicon. And that this presentation will sort of be a bit of a story about how that happened. So with all of that, I'll pass it over to Massimiliano.
Thank you very much, Mike, for the nice presentation. Thank to the Open Hardware Foundation for inviting me to this webinar. And without further ado, I suppose we can start. So from trust me to check me, the idea of the presentation is, or should be, nothing new to the audience of this webinar. Essentially, if we have a look at how the silicon, the chip design workflow is, we see that it can be a huge black box supply chain. There are third-party IPs and closed source IPs or tools everywhere. And so it is essentially impossible for any company who is working in this environment to have total control on what they are actually producing. And we believe that open source can help shedding a light on at least some of these aspects. And at PlanV, we tried to give our contribution and to put a little bit of light in some of these areas. And especially, we are focusing on the areas of RTL IPs, test benches, and verification. And we are doing this with the help of RISC-V instruction set architecture, open source IPs, and frameworks like the PALT IPs, of course, open hardware CPUs, and open hardware verification environments. And we are also working on Verilator as an open source RTL simulator. And we are also developing our own methodologies using more exotic technologies like CakeML and our own framework called Mooncake, which I will introduce you in a while. And the goal of this is, as it's written here, have a more transparent and auditable workflow and processes. So what are we actually doing? First topic is UVM and Verilator. And for probably, again, it is not necessary to describe what these two technologies are, but just to be sure, I will spend a couple of words on them. So UVM is essentially the state-of-the-art of functional verification methodologies. It is an industry standard. It is built on top of System Verilog. There are other similar frameworks which are using similar technologies like SpecMan. I think it's still used in the industry, or there is also UVVM based on VHDL, but the vast majority of verification, functional verification, is done using System Verilog nowadays, I believe. And it is essentially providing the tools which allow constrained random testing and the collection of the results into verification buckets so that you can have a nice test plan and keep it under control. Verilator is a Verilog simulator. It is a project we started several years ago. I'm not sure when it exactly started. It is an open source project. As an RTL simulator, it is extremely fast, but until 2024, it had a very poor UVM support. So essentially, if your verification environment uses UVM methodology, you cannot use, or you couldn't use Verilator as a verification engine. And we wanted to improve the situation because we believe that if you were able to use Verilator on your UVM test benches and test environments, you would essentially have the possibility to run virtually infinite test environments in parallel. And this would probably simplify and improve the verification capabilities of your team incredibly. So what we have been doing, we have worked on UVM capabilities for Verilator thanks to the Bundesministerium für Forschung, Technologie und Raumfahrt, that is the Federal Ministry of Research, Technology and Space in Germany, via the project OSVISE. We're working on this with other partners. And specifically for Verilator, what we wanted to do was adding the capabilities to handle constraint randomization in Verilator. And some months ago, we've been able to complete this step. And one of the most important milestones for this was having the tests which are collected in mics, getting Verilator started with UVM all green. And now the focus has been moved to the implementation of System Verilog assertion support and coverage. This work has covered, well, here it's written 60 pull requests, but to be honest, I believe it is more. Probably 70 was for having the constraint randomization clean, but the work in these last months, weeks, has continued, so we have done way more than 170 pull requests in total. And we've been able to do this also quite easily, and thanks for methodology which uses AI as an accelerator for the development of Verilator capabilities. So the first element in this AI accelerated workflow is what we call the gap checker. It is essentially Python based, and it uses Claude as an AI engine. Essentially via Claude, we can drive Claude, telling it how to work via a markdown file. It's called skills.md, which tells Claude which are the tools it can use in the on the platform it is working on. It takes an input file, which is essentially a YAML file, and the YAML file tells the AI engine, the AI agent, what it has to do. As an output file, it creates GitHub issues. Essentially, what it does is we define in the YAML file the features which we want to check inside, to check whether they are or not present in Verilator. As a second step, it the agent generates tests for Verilator. It executes these tests on both Verilator and on a commercial RTL simulator. For example, we've been using Questa, and it compares the results on both platforms. If tests are passing on both, then the feature is implemented and the corner case is correctly supported. If tests are failing on both platforms, then there is something wrong in the test itself, so it is not a valid scenario. If the test is passing on the reference RTL simulator and it is not passing in Verilator, then we have discovered the gap. And then after discovering the gaps, there is another agent which reviews what has been, the tests which have been selected. It checks whether there are tests which are stressing the same feature. So it simplifies essentially the test list, and it avoids duplicating, creating multiple issues which cover the same feature. And as a last step, it creates, it publishes issues on the GitHub repository for Verilator. And via this mechanism, we have been able to create 500 new tests to stress new required features for UVM. In Verilator, we've discovered more than 100 gaps, and this resulted in something like 20 pull requests. And all these pull requests have been accepted. The pull requests have been developed using another agent, which is the developer agent. So this is not so refined as the gap checker because it didn't require so much orchestration. It essentially was able to read and understand the C++ code base of Verilator, and it was able to more or less independently implement the required fixes. What I think was important and useful in this experience, in this experiment with AI and EDA tool development, essentially, were two things mostly. First, having a reference system. So we were sure that the tests which survived which triggered errors were legit tests which discovered legit issues in Verilator. And the second aspect is keeping human supervision at the end of the process, meaning that the actual issue creation was not automatically triggered, but there is a developer who has to review the claims and accept the creation of this issue or the creation of the pull request after the fix has been implemented. And in the link here, you can find some interesting information about this whole experiment with AI. So further work on UVM and Verilator. So we had, as said before, the getting Verilator started with UVM, which was passing, but we thought this was not enough to claim that Verilator was usable in for industrial, for professional usage. So we took one step further, and we try to make CORE-V verification, the test bench verification environment, which is used for the Open Hardware Foundation project, compatible with Verilator. And this is an industrial-grade test bench, and so it is a very interesting test platform for the tool itself. So there is a pull request which whose goal is to adapt this verification environment for Verilator. I think it is still open, and we are working still on it, and we hope that we'll be able to close it soon in the next, let's say, weeks. We've not only used the CORE-V verification as a test platform for Verilator, but we are also trying to use this verification environment for the verification of CPUs, which are not open hardware CPUs. So one of our clients asked us to verify one of their RISC-V cores, which is a similar class as the CV32E4 processors from open hardware. And so we are trying to adapt this verification environment for this specific CPU, and also others in the future are in the pipeline. And I think that having a more or less common platform which is able to stress and prove the correctness of the implementation of different RISC-V CPUs from different vendors is an extremely interesting thing. And the fact that this test bench is open also helps having transparent and auditable, as I was saying before, verification environment and development environment for RISC-V systems. So this slide brings us to a slightly, a different topic. This is a project. The project is named PISTIS-5. It is a project sponsored by the German Cyberagentur. For those who are not familiar with this institute, it is, in a nutshell, the German DARPA. So this institute is sponsoring research projects, research activities, who are targeting for projects which are trying to answer non-trivial issues in the cybersecurity domain. And in particular, with this project, which we're working on it together with the University of New South Wales and University of Gothenburg, we want to provide a reference architecture for a trusted embedded system. How we do this? So we are working on different layers. On the hardware layer, we are developing an open platform using open source IPs. So of course, as a CPU, we are using a RISC-V CPU, and specifically the CV6, again from Open Hardware Foundation. And then we are using several peripherals, standard peripherals, what you would expect in an embedded platform. And most of them are coming from the Pulp ecosystem. And on top of this platform, we are running the SEL4 hypervisor. And the interesting thing about SEL4 and why it is important for a trustworthy system is that it is the only hypervisor which has been formally verified. And so the level of security which is offered by this technology is extremely high. And this is why the project was interesting for the Cyberagentur. SEL4 is not easy to handle if you're not an expert. So the colleagues at UNSW and in Sweden are working on an operating system, Lions OS, which makes essentially SEL4 usable also for regular software developers. And it is essentially, Lions OS is a static operating system which is targeting embedded applications. And what is important here is that all the software which runs on top of Lions OS is confined. So functions, processes which are not supposed to talk to each other are guaranteed not to talk to each other. Data which is not expected to be accessed by a certain process is guaranteed not to be accessed by this particular process. And all these features are guaranteed by the properties which are offered by SEL4 and by technology which, as far as I know, is uniquely offered by SEL4 in combination with CVA6, which is timing channel protection. And this is a custom instruction, to keep it short, which is flushing the microarchitectural state of the CPU when there is a change in the security domain. So it makes it impossible for one process running on a security domain to extract information which are accessible by another process in another security domain by looking at the state of the system, like delays in performing some specific operations. But the interesting thing I want to talk about here is the formal verification of the software and hardware. Essentially, we are working on a methodology which allows to formally verify the device drivers which are used in the Lions operating system and the peripherals which are implemented in the hardware platform. So the problem which has been identified and the reason which kicked off this idea is that device drivers are first a major source of vulnerabilities because these are written looking at the datasheet, at the specification of the peripherals, and the specifications are sometimes ambiguous, sometimes incomplete, sometimes are wrong. And software developers have no way to see whether they are really wrong or where they are incomplete. So they have to make assumptions sometimes, and these assumptions might turn out to be wrong, and this leads to potential security issues. So open source helps us here, and it helps us building high fidelity specification. Essentially, if you have access to the RTL implementation of the peripherals, you can extract the correct specification for the peripheral itself. What we are doing is we are using this to specify the behavior of the device using formalized language, which means that we are removing ambiguity in the natural language. And then we can use this formal specification to prove both the hardware implementation and the software. So we have 2 or 3 scenarios we're working on. This is the first one. So we have the Verilog implementation of the device which we're using in the system, and we have to manually write a description of this Verilog using a formal language which is called HOL4. HOL4 is both an higher order logic language and a theorem prover. And this description is normally too detailed for it contains too many information compared to what is really interesting for software developers. So there is an abstraction step, which is done also manually at this stage. So we have a simplified description of the official specification in all 4, and we can prove that these 2 specifications are equivalent. The newly generated Hall4 specification is then used as a source for the coding of the driver, and the drivers are encoded in a new language called Pancake. It is similar to C, and it is built on top of the CakeML framework. And this allows essentially the software developer to prove mathematically the correctness of the software implementation with respect of the specifications by using Hall4 and the whole CakeML compiler and theorem proving infrastructure. We're not doing this. We are hardware guys, and we are mostly focusing on the left side of this picture. So what we have done is we've developed a tool. It is called Mooncake, just to be compatible with CakeML, Pancake. We're based in Munich. That's the reason why Moon. And Mooncake is capable of generating property specification language code automatically, starting from the Hall4 specification of the device. And parenthesis, why we picked PSL instead of system Verilog assertion, this was just a convenience choice, because the PSL language was already formalized in the Hall4 language, so it essentially was easier to prove this framework using PSL instead of developing the whole formalization for system Verilog assertions. But in principle, the same could be done also for SPAs. So what we do, we have the PSL code, and then we can use model checking tool. Can be open source, can be commercial tools. We are using at the moment Symbiosis for our project, and we can then compare we can verify that Verilog, which is the source, which we have to verify if the source and the target is compatible with the specification which we have written. This is one way of using this infrastructure, but we can think also of a different way. The right-hand side of the diagram is exactly the same as before, so I will not discuss it any further. What changes is the left hand. So instead of using Mooncake, in this case, we use it's another part of the CakeML ecosystem. It's called CakeML hardware. And essentially, it is a framework which allows to generate Verilog code starting from some Hall4 code. So we have now the verified Verilog, generated Verilog, and we have the source Verilog code. We can do at this stage an logic equivalence check between the two. And we can prove that the source Verilog is equivalent to the Verilog generated via CakeML hardware, and which is proved to be working correctly by means of theorem proving in Hall4. This also gives other idea of how to use all these tools. So essentially, it is using Hall4 as an alternative RTL language. So we don't have any more source RTL code, but what we can do is write the description and implementation of the device, of the modules we want to implement directly in Hall4, use iterative theorem proving to verify the properties of this modules, and then as a last step, generate the corresponding RTL code, which is then guaranteed to behave according to the properties which have been verified in the whole-for domain. So we are trying to use both iterative theorem proving and model checking for our projects. I know that iterative theorem proving is probably exotic to most of you, as it used to be for me. It still is, but I'm getting more and more familiar with it, at least from a storytelling point of view. So what is the difference between these two approaches? Iterative theorem proving is mostly a human intense process. It is a bit like proving mathematical theorems as we used to do at school or at the university, but supported by APC. But anyway, the steps which are required to prove the theorems must be decided by a human. It is true that nowadays with LLM and AI, there are experiments which try to automate these theorem proving steps. So it might become easier and more automated in the future, but still, I think the human capabilities in the area are essential. Model checking is essentially an automated step. One of the great benefits of theorem proving is its scalability, because it doesn't suffer from the state space explosion, which affects model checking engines. And for this reason, it is also capable of proving, and also because of the language which is used in this framework, it is possible to use more complex properties, while model checking techniques are mostly focused on local simple properties. ITP is in theory capable of also providing proofs for the complete system. So individual properties can be combined, and properties which apply globally are demonstrable. The use of theorem proving in hardware is still experimental, while model checking is an established technology for hardware verification. And yeah, so this point about link to formal specification probably is not so true, because there are, I think, for example, with SAIL, efforts are done also to create a link between formal specification and properties in model checking environments. Because of the human intense approach used by theorem proving, this is still a high effort methodology, while model checking is probably more approachable by non-experts. And well, I think I reached the end of my presentation. These are my contacts in case you want to chat in the future. And I believe it is question time now.
Hey there. Yeah. So if you have a question, you can put it in the chat. I've received a couple of questions already, which I'll just read out here for everyone. But in the meantime, if you have a question, just throw it into the chat, or sorry, not the chat, the Q&A that appears on your right-hand side of the screen. And you know, feel free to submit questions. We'll go over them, you know, as they come in until we run out of time. couple of ones that I've already received is Massimiliano, you've done a lot of work with verification environments from the Open Hardware Foundation, which is great. We certainly appreciate that, but I wonder if you've done any work with verification environments from other sources, or perhaps ones that you've created yourselves.
We have, actually. So essentially, we are trying to stress Verilator as much as we can. And so we are trying to look at what is already existing, mostly in the open repository, open project. And we believe that a very interesting source of high quality verification environment is the OpenTitan project. And so we started looking at what is there and trying to run this verification environment on Verilator. This has been a useful activity, and we have worked on, I think, 4 or 5 IPs already. We've discovered some extra gaps in Verilator, which have been already taken care of. And so we're continuing on this activity.
Great, good. I do know that there's a bit of a shortage of really high quality UVM environments that are open source. I do agree that the OpenTitan one is one of the best. OpenTitan is I wouldn't say a product. It's an open source project from Low Risk, who are also members of the Open Hardware Foundation and members of CHIPS Alliance. So I certainly agree that their verification environment is top notch. Another one, this mooncake theorem prover. This is the most interesting thing for me anyway in this presentation was a discussion about mooncake, and I was just wondering, what scale of design have you used it on? I mean, has it been some prototype designs, perhaps a little smaller just to prove that the thing works, or have you applied it to larger industrial size non-trivial IP as well?
So the goal for the project we are developing mooncake for is to have this not the whole hardware platform verified using this methodology, but we are focusing there on the Ethernet controller. So the Ethernet controller is at the moment a commercial IP, which is developed by a German company. The IP is expected to be high quality because it is used already in security critical application. So I hope we will not find bugs there, but it is for sure a very interesting testbed for the technology. So goal for the project is to have this verified. And again, we are still poaching from the OpenTitan repository. So we took, just as an example, an AES IP, and we are also applying this framework for the verification of this component.
Fantastic. Okay. Yeah, I as a verification engineer, I will say that one of the most terrifying things you can do is let somebody else that you haven't worked with take on your IP and verify it using perhaps a different approach or a different technology, and yeah, you always live in fear that these people are going to find bugs, but that's the whole point, right? So
yes.
I think your chances of finding a unique bug in that Ethernet are quite high, but I would be willing to bet that it would be a second order bug, probably not a showstopper. But yeah, if that was my IP, I'd be terrified of UMass.
So kudos to them for sharing the IP with us. And one interesting thing for the community is that if the project will be successful, they are also willing to publish the IP as an open source. So fingers crossed also on that.
That would be a real significant contribution to the open source community. Yeah, Ethernet endpoint IP would be great. There's one question that came in here. I'll just read it off. I think you actually answered this in your presentation, but maybe we could just, I'll ask the question again just to reiterate it. The flow that you're using, the iterative theorem proving flow that you're using uses PSL. Is there anything that would prevent that flow from using system Verilog assertions instead of PCL?
No, it's just work. Essentially, there was part of the infrastructure which allowed the automatic generation of PSL from Hall4, which was already available. Mm-hmm. And so we took a shortcut there and just used what was easiest to develop or fastest to develop. But the same could be done also for system Verilog assertions. It is a nice idea for a follow-up project, but we will not do it in this for the framework of the FACES-5.
Sure, and is that you use PSL because that's what the Hall4 tool already emitted, or did you deliberately select PSL?
I think we already had the formalization of PSL in Hall4 somewhere, and so we didn't have to do it for system Verilog, and this saved some time.
Perfect. Okay. All right. Well, I think that about does it for unique questions. There's a few other questions that have come in, but we've already gone over those. So I think what I'll do now is say thank you very much, Massimiliano. That was a great presentation, and we can hand it back over to Amanda at the Eclipse Foundation.
Thank you very much both for the presentation, for your time, and for your knowledge that you shared today. So just a reminder that you're going to receive the replay by email. And also we are always trying to improve those webinars. So it would be amazing if you take the time to take part of our survey. So I will also put the survey in the chat. So like this, you have access and you will also have it in the recap email. So thank you for everything. If you guys don't have any other question, we will, there's some question. There's some comment that just appear now. Mike, do you want to have a look on this?
So yes, there's a comment from Colin at Low Risk. Colin says, I work at Low Risk. I've been very impressed with the quality of work of Massimiliano and the team and look forward to continuing our relationship. So there you go, Massimiliano. You get a thumbs up. Thanks, from your thumbs up from the source right there.
There is another question from Alfredo. Did you use CORE-V-VERIF? Or did you create a new environment to add PSL, SL4, Lions OS? So these are two different topics. The CORE-V verification has been used as a testbed for Verilator, and we are also trying to use it for the verification of non-open hardware CPUs, and this is one story. Everything which is related to Mooncake, SL4, Lions OS, and that platform is not using CORE-V verification at all. Essentially, we're taking these IPs as they are, and we are just verifying a few of them using this new methodology.
Well, thank you very much for your answer. So is there any other question? We'll have the time to ask some questions. We still have a bit of time. I'll also share the survey into the chat, so you can take part of it. So if there is no more question, I would like to thank you all for attending to the webinar, and we will end. Do you have any other words, Mike or Massimiliano?
Nothing further from me. I just want to, thank everybody at Eclipse for organizing this, and thanks Massimiliano for generating this this presentation. It's nice to see this kind of work.
Thanks, Mike, and thanks for Eclipse and Open Hardware also from me, and all the attendees, of course.
So thank you very much, and see you next time.